In this video, we're going to talk about free fall, which is how an object behaves when it's thrown straight up or straight down and it's just flying through the air. Now, I want to start out with some of the things that are going to be true for every single projectile problem that you ever do. And the most important one is the fact that the acceleration is always going to be pointing straight down. And that should make sense to you because gravity is pulling down on it. So if you have something that's just in the air, maybe you dropped it or you threw it up or something like that, the acceleration is going to point down. It's not just going to sit there, but it's going to get faster and faster in this downward direction. Now, I'm not going to actually tell you why, but I'm just going to start out with the facts. It turns out that if you take an object, just a standard object like a brick or something like that, and you just drop it out a window, then what you'll notice is it will accelerate downward at minus 9.8 meters per second per second. For every second that goes by, that brick will get 9.8 meters per second faster. I'm going to actually use 10 because the number is conveniently close to 10. You'll be pretty close to the correct answer regardless of which one you use. But I like 10 because I think it makes the math problems easier. But if you've got a teacher who prefers 9.8, then just make sure you work all the problems that way. There are three big ideas that I want you to get off of this 9.8 number that a lot of my students always seem to confuse. The first of these is that the negative sign shouldn't bother you too much because it only means that gravity pulls down. But just the fact that it's a simple negative sign doesn't mean that you can skip it. So make sure that you always include the negative here or you can find yourself in a lot of trouble. Second is that the number 9.8 is just an acceleration. It's just like the accelerations we've dealt with before. Only this time it's so special because we use it all the time that we just give it the letter G. But all it means is that for every second that an object falls, it will get 9.8 faster or 9.8 slower. If you drop a ball and it falls for 1 second later, it'll be going 9.8 meters per second. If you let it fall for 2 seconds, then it'll be going 19.6 meters per second. If you let it fall for half a second, it'll be going 4.9. I think you get the idea. The third point is the idea that the 9.8 can be a two-way street. If you have an object that's going down, if it's moving downward, then gravity will make it faster for every second that goes by. So if it falls for 1 second, you'll have a speed of 9.8, like I was talking about a moment ago. But what if you're going in the upward direction? If that's the case, then you will get 9.8 meters per second slower every second. So you have to be careful and really pay a lot of attention to what direction velocities and accelerations are in these problems, or you can find yourself in a lot of trouble. Well, that was a lot of writing and not a whole lot of showing. So let me show you what I'm actually talking about when an object falls. And one of my favorite classical examples of someone falling is Wile E. Coyote from the Roadrunner cartoons. If you haven't seen those, you gotta check them out. They're pretty great. Now, what we're going to look at is what his flight will look like when he falls off a cliff like he always does when he's chasing after the Roadrunner. It's not quite as simple as an object going at constant speed because he's going to be accelerating downward. Let me give you kind of a visual of what it would look like if he fell off a cliff. Now, what we're going to do to study this motion is we're going to pretend that we have sort of a strobe camera. I'm sure you've seen a strobe light before where it flashes a certain number of times every second. We're going to have a camera that sort of works in the exact same way. So we'll have a camera program so that every half of a second, it'll take a photograph of where he is, and it'll put all those photographs together. So when time is equal to 0, the camera takes its first photograph, and he's at the top of the cliff. At 0.5 seconds, he hasn't actually fallen very far because he hasn't had a lot of time to speed up very much. So he's actually quite close to the top of the cliff still after half a second. At 1 second, you can probably start to see that he's beginning to pick up speed, and he's traveling a greater distance in the same amount of time as before. Now, after our camera's taken 5 shots of his entire fall down the cliff, you notice that the pattern is very interesting. Every sequential photograph that we take, he's traveled a greater distance since his last photograph. He's getting faster as he falls down. It's not just the same amount of distance over each half a second. It's getting bigger and bigger as he goes. In fact, if I wanted to, I could even draw arrows to show the velocity of how he's getting faster as time goes on. And later, we're going to calculate specifically how much time it takes him to go down the cliff.